Welcome to the 313 Detroit Engineering. If you enjoyed this video, please hit the like and subscribe buttons below. Here in the 313, we're going to talk today about bipolar junction transistor switch design. There is a long way between datasheet values and real world characterization values. Today, we are not going to go through the actual characterization data that form these rules of thumb. That's coming in the next video. But I will tell you this, the datasheet values that you see for most bipolar junction transistors, you can just throw them out. Because if you try to design around those characteristics in the datasheet, you're probably not going to be able to get a good design. But if you design around these design rules, which came from hundreds and hundreds of parts that were characterized, you're going to guarantee good design rules. To go into the cutoff region, where we take a BJT transistor and we shut it off, we're going to make sure that our VBE voltage, our base emitter voltage, is reverse bias. And over automotive temperature from minus 40 degrees C to 100 degrees C, if we push the VBE below 300 millivolts, we're not going to have any collector current to worry about, only leakage. If we're trying to saturate the part and we get our force beta, collector current divided by base current is equal to beta, if we get that equal to 30, we're going to force the collector emitter voltage, regardless whether you're between minus 40 degrees and 100 degrees, below 0.1 volts. And finally, in the active region, we're going to show that you want to transition between that region as fast as you possibly can to avoid switching losses. Again, today we are not going to show the characterization data. That's at the next seminar. We're going to show these rules are solid for great design, and the next seminar we're going to show you where the rules come from. Today in the 313, we're going to be talking about bipolar junction transistors and how to use these transistors as switches. To use them as a switch, we have to turn them on, put them into saturation where we get full collector current flow. And we're going to have to learn how to shut them down where we get no collector flow. Put them in that cutoff region, we call it. Bipolar junction transistors can be used as high side switches where we're trying to take the voltage source and get it over here to the load at the collector with as little VCE drop as possible. That's our high side switch. That is formed by using a PNP transistor. Likewise, we also have what's called a low side switch with our bipolar junction transistor. In this case, we're trying to get as much current through the load as possible by bringing the collector voltage as close as we can to the emitter voltage. This is called an NPN transistor, NPN. The transistors that we have selected today for this example of how to turn on and turn off a bipolar junction transistor are the MMBT A56, the SOT23 package of what's shown here, and its brother from another mother, the MMBT A06. These parts, although in a SOT23 package, can handle a half amp of DC current through the collector and have a collector emitter breakdown voltage of 80 volts. These parts can be tied up to battery with no fear of breakdown from load dump. Bipolar junction transistors are three-terminal devices, emitter, base, and collector, that are formed by two PN junctions. If we are going to turn this transistor off where we get no collector current, we'll have to go into what's called the cut-off region. We're going to turn this bad boy off. To do that, we must reverse bias both of these PN junctions, the base emitter and the base collector. If these junctions are reverse bias, we get no collector current flow. If we want to go into the saturation region where we get maximum collector current flow and we have this bad boy turned all the way on, we are going to have to forward bias both of these PN junctions, both the base emitter and the base collector. With these junctions forward bias, we're going to get maximum current flow through the collector. That is saturation region. And finally, to go from cutoff region to saturation, you must pass through the active region. That's the case where the base emitter junction is forward bias, but the base collector voltage is reverse bias. More on that to come. Let's get into the real world, the 313. If we're going to turn off this bipolar junction transistor and go into cutoff, how do we guarantee that we are going to have the base emitter junction reverse bias? In the data sheet, they do not give us a VBE off value, but there is a clue in this graph right here, the VBE on. X-axis is collector current, Y-axis is VBE on. These are 150, 25, and minus 50. Most automotive design is done between 75 degrees C and 100 degrees C ambient temperature. 150 is not a real world usage profile for a transistor. If you think about it, the junction temperature is limited to 150. If your ambient's 150, you can put no power in the device. If we're looking at what it takes to turn a VBE on at 100 microamps, you can see we need to get the base emitter to about zero point 0.2 volts. It would reason to stand if we want to shut this part off, we have to get below zero point 0.2 volts at an ambient of 150 degrees C. But like I said, 150 C is not the real world. Let's figure out what is. If we're going to put a BJT transistor into cutoff in the real world, we're going to have to first consider the effects of temperature. Minus 40 degrees up to 100 degrees C are real world temperatures that we're going to see in automotive and in many other applications. In this case, you can see that we have set the VBE to zero point 0.3 volts, 300 millivolts. In that case, at 100 degrees C, we come over here and we're going to look at the collector current. We have nanoamps of current. We haven't even hit 1 microamp of current. This is close enough for cutoff. Now, why would we set the base emitter at zero point 0.3 volts? Why wouldn't we just set this supply over here to 0 volts? Well, as you know, when we're driving most of these transistors, we're using some type of microcomputer. If that microcomputer's output ever goes high impedance, for example, during reset, we can get leakage currents that will begin to energize the base emitter. In this case, if we design for maximum leakage current that will allow zero point 0.3 volts to get to the base emitter, we are going to guarantee cutoff in the real world. We're going to shut that baby down. Okay, so we can shut the transistor off. Hey, can we turn the bad boy on? Can we put it into saturation? First thing we're going to look at is what the data sheet tells us about saturation. You can see right here, they're talking about collector emitter saturation voltage of 0.25 at a collector current of 100 milliamps with a base current of 10 milliamps. That's a gain or a beta of 10. Well, let me tell you what, if this is how the transistor really worked, according to this data sheet right here, we are not going to have successful switch designs in most applications. What we're going to do now is we're going to take a look at the real world. What kind of force beta do you need to get very low VCE drops to make our switches work? In the real world, if we want to saturate this part and get maximum collector current through the part, I'm going to tell you right now, you're not talking about a force beta of 10 like the data sheet shows and a VCE drop of a whopping 250 millivolts. We're talking a force beta of 30 or less to achieve a VCE a zero point 0.1 volt or less. That is real world performance. That is real world design. You can see in this simulation, we've set the temperature as low as we can go, minus 40 degrees C. Minus 40 degrees C is minus 40 degrees Fahrenheit in the 313 and in the rest of the world. Under this condition, you can see that our NPN transistor with 100 milliamps of collector current, 3 milliamps of base current has hit a force beta of around 30, and we get extremely low VCE drops, less than 100 millivolts. Why did we set the temperature at minus 40? Because that's when the gain begins to drop, and that's when the VBEs begin to climb. The VBE temp coefficient, as we mentioned before, is about minus 2 millivolts per degree C. Gain will also drop at cold temperatures. This is the real world design. If you get a force beta of 30 or less, you're going to guarantee a VCE sat of zero point 0.1 volts. Let's continue to look at saturation in the real world. What we've done here, if we've taken this NPN switch and we're going to do a DC sweep on the input voltage, and we're going to look at a couple things. We're going to look at the gain of the device and we're also going to look at the VCE saturation voltage. Right here, we're performing a sweep from 0 to 5 volts on V1. If you take a look at the gain, when we hit an input voltage of just about 4 volts, we are going to have a force beta equal to 30. And you can see we have achieved an extremely low VCE sat below 100 millivolts. Now, here's the good news of this design rule. Even if we get an additional load step of current, we are a long way away from the active range, and we are going to keep this part in saturation. A force beta will give of 30 will give you low VCE sat, and it'll give you a lot of confidence. Even if you have a load step, you're not going to slide anywhere near the active region. Let's talk a second about the active region. To go from cutoff, no collector current, to saturation, maximum collector current, you're going to have to pass through the active region. The data sheet tells us if our collector current is at 100 milliamps and we are in the active region with a VCE equal to 1 volts, they're guaranteeing a gain of about 100. That's what the data sheet shows, but the plots tell us a different story. Even at minus 50 degrees C and a collector current of 100 milliamps, you can see the DC current gain is well over 150. Let's take a look at what happens in the real world when passing from cutoff to saturation and that time we spend in the active region. Like we said earlier, to go from cutoff, the transistor's off, you got no collector current flow, to going to saturation, where you're getting maximum collector flow, we are going to have to pass through what we call the active region. In that case, the base emitter junction is forward bias, the base collector is reverse. When you're looking at this DC sweep here, we're sweeping this input voltage from 0 volts up to 2 volts. We're monitoring the collector voltage with this plot, and we're looking at gain with this plot. You can see as we're transitioning from cutoff to saturation, the gain is relatively flat at about a gain of 200. This is the point in time when we are in the active region when the gain, collector current divided by base current, is constant. We talked about we want to spend as little time possible in the active region right here. When we're passing from saturation, where we have maximum collector current flow, you can see ICs up here at 100 milliamps, into the cutoff region where IC is equal to 0, we want to spend a smallest amount of time as possible in the active region. And the reason because is switching losses. When we're switching from saturation to cutoff, we have what's called switching losses, where the power in the BJT goes to the highest levels. Right here, I've changed our transistor from an NPN to a PNP. And what I'm showing here is when both junctions are forward bias, the collector voltage is awfully close to being equal to the emitter voltage. There's very low VCE drop. When we reverse bias both of these junctions, we're in cutoff, and you can see that our collector voltage drops to 0 because we have no collector current. But as we pass through the active region where the base emitter junction is forward bias, but the collector base junction is reverse bias, we begin to get high power losses. Again, this is called switching losses, and this is why we want to spend as little time as possible in the active region. You can see in saturation region, although the collector currents are high, the VCE drops are very low. Therefore, we have low power dissipation. Cutoff is easy. There's no current going through the load. Although we have the highest VCE because we have no current, the power dissipation is going to be 0. But the switching losses going between saturation and cutoff while we are in the constant gain region or the active region are going to be maximum. This is why you see the power dissipation shoot up when we're in the active region, and we want to spend as little time there as possible. Here's a summary of how to go from cutoff to saturation in the real world. We want to keep it real. We want to keep it in the 313. We need solid design rules, and I'm going to summarize right now how to go from cutoff into saturation without having any problems. Number one, cutoff region in the real world. If you keep your base emitter junction below 0.3 volts, even at 100 degrees C, you're going to have no collector current to speak of. The only concern we would have here is leakage, right? We always have to be aware of leakage and if it's going to impact our circuit. The next region, saturation, if we guarantee a force beta collector current divided by base current of around 30, we're going to drive the VCE down below zero point 0.1 volts, and we're going to get this switch really to conduct current like we want it to. That's the saturation region. Remember, we want a force beta of 30 in case we get any load step, we're not going to slide back into the active region over here. Finally, the active region, when the gain is constant, we have a constant gain situation and we're transitioning between cutoff and saturation. We've got to watch out for those nasty switching losses, power dissipation. I'd like to thank you so much for tuning in to the 313 today. Again, if you like this video, if you've enjoyed watching it, please hit the like and subscribe button below. Thanks and have a great day in the 313.